On from this last video, we're going to talk about the variation of diagonalization that is called orthogonal diagonalization, and it's really not that much different. The idea is that first off we have definition. A matrix, which we're going to call O here, is called orthogonal if the inverse of the matrix is the same as the transpose of the matrix. So whenever this happens, it is called orthogonal. And once you have the idea of orthogonal, then you have the following result here. So the orthogonal diagonalization of a matrix A is when you write A equals O D O inverse, where D is diagonal, O is orthogonal, and since it's orthogonal, it's the same thing as saying O D O transpose, since the inverse is the same as the transpose for an orthogonal matrix. Okay, so this here is the definition of it, and just to remind you, it's very, very similar to the regular diagonalization. The only difference is that before we were allowed to have any matrix P here, and now we want it to be an orthogonal matrix. So that is literally the only difference between a regular diagonalization and an orthogonal diagonalization. Now, we need to look at an example where this happens. And so let's see this here. By the way, just a little comment is something that you may or may not have learned in the past is that not every matrix can be diagonalized, right? Some matrices can and some cannot. It depends on properties of the matrix that maybe you went into before, maybe you didn't. Similarly, some matrices can be orthogonally diagonalized and some cannot. The one we just did cannot be orthogonally diagonalized, but let's do one that can be here. So let's look at the following here. Let's let my matrix A be 4, 2, 2, 1. So it's going to turn out that this one is orthogonally diagonalizable. So let's go ahead and do the steps here. We're going to take our determinant of A minus lambda I, and you're going to get 4 minus lambda times 1 minus lambda minus 4. It's going to work out to be lambda squared minus 5 lambda. You're going to set that equal to 0 here. And so then what we have here is lambda is 0 and 5. So I'll go ahead and look at each one of them. If I have lambda is 0, then A minus lambda I 0 is going to be 4, 2, 0, 2, 1, 0. RREF that. We're going to get this here. So x plus 0.5y equals 0. X equals negative 0.5y. And so this right here is going to be my eigenvector for 0. For lambda is 5. We would have the following here. We would have negative 1, 2, 0, 2, negative 4, 0. Again, RREF that. We get x minus 2y is 0. So then x is 2y. So we get 2, 1. And I want to point out something here. You can check that these two vectors are going to be perpendicular, orthogonal to each other. So turns out that that is not a coincidence. We can prove a theorem in this section that given the right matrix A, it will happen. but for right now I'm pointing it out. The only thing is, in order to be an orthogonal matrix, we need to not be just perpendicular to each other. We need to also be unit vectors, so length 1. So you're going to take your negative 0.51 and you're going to divide by the length of it, which, let's see, negative 0.5 squared plus 1 squared. And if you do a little bit of work here, you're going to have negative 1 over root 5 and 2 over root 5. And when you have 2, 1, and you divide by the length, you will have 2 over root 5, 1 over root 5. And then once you have this, then your orthogonal matrix is just going to be those two eigenvectors put together, using as columns here. And then finally, your orthogonal diagonalization is we put these here, and then my diagonal has my eigenvalues, and then that same matrix inverse, which is also the same as the transpose. I won't work that out right now. So what I'm trying to show you here is when you're trying to do orthogonal diagonalization, it's basically the exact same as regular diagonalization. One extra step though, of when you get your two eigenvectors, you need to make them into unit vectors. That's all. And then you got your O, and then you're good. So that is how you do an orthogonal diagonalization. And you should really expect a question that asks you to find the orthogonal diagonalization of a given matrix. So next up, we'll talk about when this can even happen. Again, I said earlier it can't always happen. Turns out there's a nice theorem that will tell us when it can.